Today's topic, I will talk about estimating coastal water turbidity using VIIRS nighttime measurements. My major advisor is Dr. Chih-Wei Huang, and my committee members are Dr. David Na and Dr. Brian Burns. Firstly, I will talk about the background, and then its objectives in these studies, then data and method, results and summaries, and the final is my conclusion. Turbid water is defined the water that contains the suspending sediments, causing it to be deficient in clarity. It is apparent that a water's color can be visualized, so people can identify whether the water is turbid or not. In this study, water turbidity is defined in the ISO 7027, published in 1999. It is based on the measurement of the ratio of a suspension formation to the same ratio of the 90-degree scatter light. The unit of the water turbidity in this study is FNU, formation nepherometric unit. In this image, so you can tell the water's color and the corresponding water turbidity. Simply speaking, we not only visualize different water, we can quantify water turbidity according to the amount of light passed through the water. It is easy to visualize the water, whether it is turbid or not. The boundary between clean water and the turbid water is sediment fronts. In estuaries, these sediment fronts can be easily to be visualized. The sediment fronts are usually associated with sediment transport. The magnitude of the sediment transport can be increased by natural process or human activities. In some cases, sediment could be a pollutant where the environment needs clean water. This includes life that is sensitive to the sediment inside the water. In other cases, it could be beneficial, such as when the sediment source is needed to maintain a delta's wetlands. Without the cycle of the new wetland growth, a delta is going to shrink. So measuring the time and distance of the sediment transport and quantifying erosion is very important for coastal engineering. Traditional turbidity measurement have high accuracy. However, it takes time and manpower to provide an overview in the area. Mapping turbidity using remote sensing is useful for scientists to monitor water turbidity in the real time. Satellites usually don't directly measure turbidity. Instead, algorithms are provided to estimate turbidity. Usually, different water use different algorithms. In 2009, Nature et al. They published the first multi-sensor turbidity algorithms. Following their work, Dogliotti et al. In 2015 published a turbidity algorithm for global and multi-sensors. The image above reference some results. Other studies have covered the other oceans. But so far, all of these turbidity algorithms, they are calibrated in the daytime, and no nighttime turbidity algorithms is provided. We know because we have many observations in the daytime, but we have no data in the nighttime. Satellite images are very easy to be blocked by the clouds or biased by the sun gleams. It is hard to measure water turbidity under this condition. However, those sediments, they are still inside the water. They do not disappear. If we can have more observation, for example, nighttime data. Then we can have water turbidity every day. When the daytime data are not available, the nighttime measurements of water turbidity can be used to estimate sediment fronts or prediction in the coastal models. VIIRS is one of the 5 sensors carried on the National Polar Operating Satellite, launched by 2011, and it has 22 channels. One important feature of VIIRS is it can observe in the daylight band, providing visible images at night. After 2014, VIIRS is the only satellite instrument to provide a visible image at nighttime. During the night, we know it is dark. However, the visible light is still pretty common. The most significant light source from human activities are lights from the cities, fish boats, and oil platforms. Other objects like sea ice and sediment inside the water can be observed through the moonlight. Currently, there is no observing system can provide ocean color in the daytime. However, visible daylight band data provided some possibilities. The advantage of this system is that we can have 2 data a day, one during the day and one during the night. There's already literature correlate the water turbidity with visible red bands. Daylight band covers a wavelength from 0.5 to 0.9 micron, including visible red band. Therefore, VIIRS daylight band should be able to quantify coastal water turbidity. This was shown in 2018 when 3 case studies were published by Chih-Wei Huang. They used a daylight band irradiance ratio to explore the diurnal movement of the sediment fronts. However, there are still some unknowns. Daylight band provides some possibility. However, when compared to the daytime product, how large of a contribution to turbidity information would daylight band? And also, because daylight band covers a wavelength from 0.5 to 0.9 micron, including visible red band and near infrared. So how well can daylight band be used to estimate coastal water turbidity, and how many nights can be retrieved within a lunar cycle are still unknowns. The goal of this study is to fully explore VIIRS daylight band's capacity to estimate water turbidity at night. There are 2 objectives in this study. The first one is to compare the usable water pixels from nighttime imagery and daytime images. This comparison will tell us the daylight band contribution in terms of turbidity estimation. The second is to estimate turbidity by using daylight band data through the comparing with daytime turbidity and developing turbidity algorithm for daylight band. In this study, I will focus on northern Gulf of Mexico, where the coastal water continuously receive continental waters from the outflow plume of the Mississippi River, making this region is ideal for studying water turbidity. The comparison between daytime and nighttime images will be performed in the entire region. The 2 red boxes shows Atchafalaya Bay and Mississippi River Delta. The daylight band images with identifiable turbidity pattern will be identified in these 2 images, and developed turbidity algorithm will be applied in these 2 regions. So here's my data. I use data from 2016 to 2017. VIIRS daylight band data will be mainly used to identify turbidity pattern at night and access to develop a turbidity algorithm at night. VIIRS daylight band data can be blocked by clouds. Cloud masking can be made through the combination of different products. For the daytime data, I use water reflectance from 671 and 862, which are in the visible red bands. These two variables will be used to derive daytime turbidity. To simplify speaking, I will say red reflectance for these two variables. So here's the flow chart of the daylight band contribution for turbidity estimation. Firstly, daytime water pixels can be counted through the red reflectance images. For nighttime water pixels can be calculated through the daylight band images after land and cloud masking. The figure in the bottom shows a sample. The black area in the top and the bottom shows the land masking and cloud masking. The region in between shows the water pixels. The water pixels will then be used to count the daylight band contribution. There are two different contributions. The first one is water pixels in all images. And this one will tell us daylight band's ability in detect the water pixels. The second one is daylight band contribution for water pixels in images with turbidity pattern. This estimation will tell us the contribution in terms of turbidity estimation. Therefore, to calculate these two contributions, we use two different equations. The first one is equation 1, calculate the water pixel in all images. The second one, calculate the water pixel in images with turbidity patterns. The difference to be noticed here, the difference between equation 2 and equation 1 is the equation 2 also removes the sun gleam and moon gleam pixels because those pixels could possibly introduce some uncertainty in estimating turbidity. So those pixels, they are removed. Here's my result. This slide shows the daylight band contribution in equation 1 for all water pixels in all images. The blue area shows daylight band contribution. The red area shows daytime contribution. The x-axis shows months of the year, and y-axis shows percentage. In 2016, the daylight band contribution, the mean is 36%, and in 2017, it is around 49%. The difference is because different cloud masking used in these 2 years. Because VIIRS standard cloud product is only available after March 2017. So before March 2017, I have to develop my own algorithm to do the cloud masking. Overall, the mean daylight band contribution is 42.9%, which it is significant when compared to the daytime turbidity. This slide shows the daylight band contribution in equation 2, which counts the water pixels in images with turbidity pattern. From 2016 to 2017, there are 87 images with identifiable turbidity pattern and 46 images with turbidity pattern, but they are blocked or obscured by the small clouds, hard to separate. These images are then organized with the day and the corresponding moon phase, and then in the above histogram, and then quantified. There are 118 images are within 4 days and before after full moon. 15 images are outside this range. In my study area, there are total 42 images in the full moon. And there are 22 images. In these 42 images can be observed with the turbidity pattern. Therefore, there are 42% available images occur in this period with sufficient moonlight illumination. The equation contribution from equation 2 can be further looped into the two regions. They are Mississippi River Delta and Atchafalaya Bay. The x-axis is months of the year. The y-axis is percentage. The red color represents the Atchafalaya Bay. The blue color shows Mississippi River Delta. The mean in the Mississippi is 32.8%, and the mean contribution in Atchafalaya Bay is 36%. The lowest value is 5%, but highest value it can reach to 83%. The difference compared to the previous result is because the cloud shifting. Because when we look into a smaller region, the cloud shifting becomes a more important factor. Cloud can move very fast. It can be totally cloud-free at the night, but blocked by the clouds in the following days. Overall, when combine these two deltas, the total daylight band contribution is 32.5%, with mean standard deviation 14%. So here's my summary. For daylight band contribution for all water pixels in images, it contributes 42.9%. Factors that are causing this disparity comes from two different cloud masking methods in this study, introduce more than 10% difference. Additionally, the light for daylight band images, the lights from the fish bowls and oil platforms are very strong. Those pixels, they are removed in the daylight band images, but remains in the daytime images. For daylight band contribution, in terms of turbidity estimation, the contribution is 32.5%. One factor that influences daylight band's ability to detect the turbidity pattern is the amount of the moonlight at the night. And most of the available images, they are within the 4 days before and after the full moon. After remove sun gleam and moon gleam pixels, daytime observation still contributes more turbidity pattern detection. And also, daylight band cannot detect the turbidity in each single day, even when the moonlight is available. This leads to the speculation that the turbidity pattern is only identifiable in the certain range of satellite view angle and moon luminance angle. The final factor that influences this contribution is the variation clouds, which becomes more significant when we zoom in the area. In the following slide, I will talk about the development of the daylight band turbidity algorithm. The ultimate goal is to use daylight band data to estimate nighttime turbidity by matching daylight band reflectance and daytime turbidity. Daylight band reflectance can be made through the Lunar irradiance model and nearest neighbor approach. For daytime turbidity, it can be made through the two red reflectors with a turbidity algorithm. After match the daylight band reflectance and daytime turbidity, we can find the algorithm to estimate nighttime turbidity. For the daytime turbidity algorithm used in this study, I used the algorithm provided by Nature et al. 2009 and revised by Turbidity et al. 2014 and 2015. T is turbidity, and AT and CT in this equation, they are wavelength-dependent calibration coefficient. The rho W here is water leaving reflectance. In Turbidity et al. 2015, they further revised the equation to combine the turbidity with a weighting function. The weighting function changed from 0 to 1. After applying this equation, the range of the turbidity can range from 0 to 1000 FNU. For daylight band reflectance, it can be calculated through this equation. Top of atmosphere over TOA daylight band reflectance. R is the daylight band reflectance, and L is the radiance from the daylight band. The F is the lunar irradiance. The theta is the lunar length angle. To calculate the lunar irradiance, I need a model, which is from Miller and Turner in 2009. To remove the influence from aerosols, I use nearest neighbor approach from Hu et al. 2000. In order to calculate the top of atmosphere daylight band reflectance, I need a downwelling lunar irradiance. In 2009, Miller and Turner shows a way how to calculate the lunar irradiance based on several inputs listed in this chart. However, their output doesn't provide any geolocation information. Therefore, I modified the model to calculate the lunar irradiance at a specific date, time, and place.